Well, thank you for having. Okay, thank you for having me and for inviting me to give this talk today. So the Game of Cycles is joint work that I did with some collaborators at ROOF in 2019. ROOF stands for Research Experiences for Undergraduate Faculty. On the left-hand side, you'll see a picture of my collaborators in which Dr. Francis Su here from Harvey Mudd College introduced the project, the Game of Cycles. On the right side, you see us continuing to work through COVID, and we take a Brady Bunch picture because it was like, why not? And so we took a Brady Bunch picture. So today what I'll talk about is I'll first give some definitions, and then I'll tell you the objective of the game, and then we'll do an example together. And then I will talk about the results for various game boards. And lastly, I'll talk about this field board theorem, which we'll know more about that as we move forward. And then finally, I'll talk about some further questions and other directions that this project may go in. The Game of Cycles is a game that is played on simple connected planar graphs of vertices and edges. It was introduced by Francis Su in his book, Mathematics for Human Flourishing, that came out in January 2020. But we worked on the project beforehand. So we started working on the project in August or June of 2019, but we couldn't say much about the project until the paper came out, or till the book came out in January of 2020. A few definitions. Given a planar graph, we define the following on the graph. We say that a planar graph of vertices and edges, it divides the plane into regions that we call cells. If a graph together with its boundary cells is called a game board. We define a cycle cell to be a cell in which all of the directed edges of that cell are in the same direction. And then we say that a vertex is a source if it has all of its edges pointing away from it. And a vertex is a sink if it has all of its edges pointing towards it. So here at the bottom, we have the cells C1, C2, and C3, and then we have this cycle cell. The objective of our game is we're going to want to be able to create these cycle cells using some rules. We have a source here as well as a sink. So what are the rules of the game? The Game of Cycles is played by two players in which they take turns marking unmarked edges with an arrow pointing in one direction or the other. The arrows must obey what we call the sink source rule, which means that a player is not allowed to create a sink or a source at any vertex. Each edge can only admit one arrow, and arrows serve the same function regardless of who marks them. Players must make a move if they have a move available to them, so they cannot skip their turn. With this, the Game of Cycles is actually an impartial game because all of the moves are available to every player. The objective of this game is to produce a cycle cell. The first person to produce a cycle cell wins the game, but if the game continues and it ends without a cycle cell being produced, then the person to make the last move is declared the winner of this game. So let's look at an example of a game board in which it already has some arrows already marked. Here, I think there are 9 arrows marked. On this game board, we can see that at vertex B, it has a source. At vertex I here, there's a sink. But also what's more important to note is that at this edge, the edge or the cycle from E, D, G, H, while it looks like it could be a cycle cell, it is not a cycle cell because it has this edge EG that is between it. But if I was to mark this edge from G to E, now I have produced a cycle cell. And since now there are 10 edges, that means that player 2 wins this game because we're taking turns where player 1 starts first. Let's look at an example of a game board. I want to take a moment and actually just play the game. So I will ask anyone to volunteer to either be player 1 or player 2, and I will be the other person.
I can play. I just need to. Oh, there's someone else playing. Okay, that's even better.
Oh, someone else is playing?
I can go.
Okay.
I can be player 1.
Okay, you could be player 1.
Yeah.
As player 1, you could just tell me which direction you would like to mark the edges. So if you say B to A, I'll mark the arrow from B to A.
Okay. B to A.
Okay, you marked B to A as player one. As player two, I am going to mark the edge D to C.
Okay. Let's do A to C.
So then if you do A to C, then at this particular point, you've created what we call a death move, which I'll tell you about it a little bit later. But here, I'm going to mark from C to B and win the game because it creates the cycle cell here.
That's fair.
Yes. All right. So, yeah. Should we do another example?
Yeah, someone else want to jump in?
All right. So I'm going to erase them all.
I'll play.
Okay.
Okay, I'll start with B to C.
Okay. B to C. Okay. And so then I'll do, I'm going to do A to D.
Okay. I'll do A to C.
A to C. Okay. So now that you've done A to C, I can't mark D to C, right? Because then that creates a sync, or that creates a sync. So I'm going to mark B to D.
I see. So I would need to go A to B, right?
So then if you mark, yes, you'll need to mark A to B so that we wouldn't have a source. So if you mark A to B, then I can make a move and I should probably mark,
Oh no, yeah, there's a source at A now.
oh yeah, there's a source at A. So actually you can't mark that one. Actually, there are no other errors. There are no others that can be marked.
Yeah.
And then this is a player two win. All right, so let's talk a little bit more about this. So here, notice here we had what we consider to be an almost source at B and an almost sink at D, which I'm going to detail on the next slide. So here are a few definitions. An almost source is a vertex in which all of the edges are pointing towards it except one edge, and that edge is unmarked. And then an almost sink source is a vertex in which all of the edges are marked away from the vertex except the remaining edge, which is unmarked. And we define an unmarked edge to be markable if it can be marked with an arrow without violating the sink source rule. We say that an edge is unmarkable if it's incident to two almost sinks or two almost source. So for this example, I think we just actually created this graph in some way. Here we have that on this K4 board, we have an almost sink at vertex A and vertex D here. And then we have almost source vertices at vertex B and vertex C. But the edges BC and AD are unmarkable because in either direction, if we mark them, we will have either a sink or a source at one of the vertices. So with this, we ask the following question. Given a game board, who has a winning strategy and what is that winning strategy? We first need to define a strategy. A strategy is a specification of moves to make in any situation. We define a winning strategy to be a strategy in where one player wins no matter how the other player plays the game. And then we say that a player has a deterministic win if they are able to win the game without using a strategy. Looking back at the K4 board, we say that on the K4 board, player 2 has a winning strategy, and we're going to detail the winning strategy for player 2. So here, player 1, after player 1 makes their first move, player 2 should respond by marking the unique edge that is not incident to the first marked edge. That's just the first part of their strategy. If we look at board 1 here and board 2 here, These are the possible boards that result from either player one's move that results from player one's move and player two's move after their first moves, up to some rotation and reflection of the vertices and the edges of the graph. In board one here, if we look at this, or well, before we get to that, I should say what an unplayable edge is. We say that an edge is unplayable if by marking it, the next player can create a cycle cell and end the game. So in board one, we have that this edge ED, or this edge AD, it is unplayable because if player one plays this edge AD, if they play the edge from D to A, player two can create a cell cycle by playing the edge from B to D. But also, if player one plays the edge from A to D, player two on the next turn can create a cell cycle by playing the edge from C to A. Now, an edge that's unplayable, it may become playable later in the game, given that some of the other edges are marked. So unmarkable is not the same as unplayable. So now what should happen? Suppose player one and player two make their next moves in which it doesn't result into actually ending the game. Then it'll look like either boards 3 or 4 here. In board 3, the remaining edges are unmarkable, and so player 2 will win this game. However, in board 4, player 1 is forced on their third turn to make what we call a death move. A death move is a move in which the next player immediately wins by either creating a cycle cell or being the last person to make a move. So in board 4, no matter which move that player 1 makes, it's going to create a death move for player 2. It creates a death move, and then player 2 can win this game. So from here, we can see, if we go back to the original boards 1 and 2, so we just showed how the game can be played on board 1, the game can be played on board 2 in a similar manner. And you'll get the same results, so that player 2 would have a winning strategy. So with that, let's talk about cycles. So here, consider a cycle graph, CN. First, I want to talk about this lemma that we have. If you have a cycle board CN that has no markable edges, then the number of unmarkable edges must be even. Suppose not, right? So first, we have the following. We should prove the following. We have that if there are markable edges, then they cannot, then if there are no unmarkable edges, then, if there are no markable edges, then there cannot be two unmarked edges adjacent to each other. If that is the case, then we would have something that looks like vertices A, B, C, in which we have two unmarked edges that are next to each other. But we know that we can mark an edge because at vertex B, we don't have an almost source or an almost sink. So this tells us that we could mark an edge, and so we can mark the edge BC. So it's possible to still have that case. Also, we have that two adjacent marked edges must be pointing in the same direction, because if not, then we have a source or a sink, and we cannot have that in our graph. Lastly, I want to talk about the unmarkable edges. The unmarkable edges, they actually divide the boundary into unidirectional marked chains, and the directions change at each unmarkable edge. So here, if you're looking at the unmarkable edge, this unmarkable edge, you can see that the directions will change at that edge. And using that, if we start at any edge, we know that if we move around the cycle, we have to come back to that edge. And so this tells us that the number of direction changes must be even. And so since the number of direction changes must be even, and the direction changes only occur at unmarkable edges, then the number of unmarkable edges must also be even. So using that lemma, we have the following theorem. If you have a cycle board, it is entirely determined by parity. So if n is odd, then player 1 wins, and it's deterministic. If n is even, then player 2 wins, and it's deterministic because the number of unmarkable edges come in, I say pairs, but the number of unmarkable edges is even. Now, consider the cycle board with the chord. we have the following theorem. So if you have a cycle board and it has a chord that's connecting two non-adjacent vertices, if n is even, then player 1 has a winning strategy. And if n is odd, then player 2 has a winning strategy. I'm going to detail the strategy to you for player 1. So suppose that n is even. Well, if n is even, then player's 1 strategy is to mark the edge, the chord. So player 1 should mark the chord. So let's say, for example, player 1 marks the chord from A to B. Then player 1's next move, so after player 1 makes their first move, player 2 can make any move. But player 1's next two moves, so their second and third moves, should be to ensure that on the vertices that are, or on the edges that are incident to A and D, there's a direction change at one of those edges, so that the edges are marked in the opposite direction as the direction from the edge from A to B. And they can ensure this because no matter what, if player 2 marks an edge that's going towards the same direction as the vertex from the edge from A to B, then player 1 can just mark it the opposite edge in the opposite direction. So for example, since we have the edge AB marked, player 1 should make sure on their second and third turns that either the edge from A to C is marked or the edge from A to E is marked. And so that's for just vertex A. But for vertex B, they need to make sure that the edge from D to B is marked or the edge from F to B is marked. And by doing so, what this does is it actually creates direction changes at these vertices at B and A. And so using that information, we will have that the number of unmarkable edges will be even. And so now after player 1 has made their second and third moves, their only strategy is to make sure that they do not have a death move. So they could just continue to play the game, ensuring that they do not have a death move. If they create a death move, then player 2 will win the game. But ultimately, the game will end with player 1 either creating a cell cycle or being the last person to make a move. So how can we ensure that player 1 does not, or that player 1 is able to not create a death move? Well, suppose not. Suppose player 1 has to create a death move and player 2 automatically wins the game. Well, looking at our argument, we know that the parity tells us that there are an even number of moves that can be made, but also the number of unmarked edges is also even. But if this was not the case, then that would tell us that we would have an odd number of unmarked edges, and that goes against the lemma that we had on the previous page. So we have to have that case. So what we can assume here is that the game ends when there are no markable edges. And so there are exactly 2 directional changes at A and B. And also that here outside in this cycle, there's a number of even directional changes and a number of even directional changes here as well. And so player 1 can, in fact, win this game. Now, this is a winning strategy. It's not deterministic, and we can see that it's not deterministic for player 1 by looking at the following graph. So suppose that the edges were marked in this way. If the edges were marked in this way on our graph, then what we have here is the following. Well, there's only one directional change, and it happens at the edge from A to C. So this tells us that there are an odd number of unmarkable edges, and thus if n is even, then thus player 2 would have the winning strategy in this case. And so it's very important for player 1 to be sure that they have these that they create something like on the previous page with those edges in the directions. Now for player 2, if n is odd, player 2 has a similar strategy that they could use to show that on a cycle graph with the chord, player 2 would have a winning strategy. What questions do we have about this?
Hi, could you recap what you mean by a direction change at a vertex, please?
Yes, so direction changes, if I go back to, or I could just do it here. So if I draw a graph on a cycle, the direction changes must occur at the unmarked edges. And so what I mean by the direction change is that if I have this edge and this edge marked, then I have a direction change here because I'm going in a counterclockwise direction, but then now it's clockwise. And so this is a direction change.
Thank you.
And it only occurs at the degree 2 or at the unmarked edges because this is a degree 2 graph. All right. All right, so now let's look at another type of a board that contains cycles. So consider a cycle graph, CN, that has an additional vertex, but this time that additional vertex actually is an internal vertex, which we called A, and it's adjacent to two vertices that are on the cycle graph CN in the following manner. It's adjacent to two adjacent vertices. So you have this graph here. If N is odd, then player 1 has a winning strategy. And if N is even, then player 2 has the winning strategy. And the strategy follows from the same lemma that the number of unmarkable edges is even. But also, when N is odd or N is even, depending on whether player 1 or player 2 has the winning strategy, that player can ensure that this triangle cell is not cyclable. And so once they're able to ensure that this triangle cell is not cyclable, then we look at this largest cell cycle that we have out here, and we're going to use the fact that the number of unmarkable edges come in pairs, or there's an even number of unmarkable edges. And so that would give you the winning strategy for player 1 or player 2, depending on the parity of the graph. But with that, I want to talk about graphs that have rotational symmetry. So if you have a graph that has a 180-degree rotational symmetry, we can actually talk about who can win this game. In this first board, we call board A, player 2 has a winning strategy. And in the second board, board B, player 1 has a winning strategy. And it's all based off of this mirror reverse strategy, which says the following. First, if it's ever possible to win by completing a cycle, do so. That's the first thing that you do, right? Because we are always thinking about optimal play here. But if it's not possible, then the player who has the winning strategy, they are going to mirror the other player's strategy by first observing the most recent move that the player made. So if they move from vertex I to vertex J, then the player who has the winning strategy is going to play the edge J prime to I prime, which is the partner edge, with its arrow reversed. By reversing the arrow, it ensures that we don't create a death move by creating these cycle cells or almost cycle cells. And so it ensures that. But also, what we get from this mirroring strategy is that so if player 1 is creating, let's say, for example, on board A, player 1 is creating these almost sinks, then player 2 is going to be creating almost sources because it's playing in the opposite direction. And so on board A, because it's completely symmetric, then player 2 has a winning strategy. But on board B, it is symmetric, but this edge EF here, and when you do the 180-degree rotational symmetry, it gets rotated back, it's back to itself. And so player 1 should always play the edge EF first, and then after that, they're going to do the reverse mirror strategy for player 2. And so they sort of become like the new player 2 in this game once that edge has been marked. But it's not always the case that we can use the mirror reverse strategy for grain boards that have 180-degree symmetry. For example, if you consider this graph, well, this graph has 180-degree symmetry, but the strategy fails. And I've listed out here how the strategy would fail. So if player 1, for example, marks the edge from B to A, then player 2 will mark the edge from C to D using the reverse mirror strategy. C to D. And then player 1 now can mark the edge from A to E, which is perfectly fine and does not create a death move. But here, player 2 would mark the edge from E to C using the reverse mirror strategy, but this creates a death move because no matter what happens, player 1 can either play the edge from D to A or the edge from C to B and create a cell cycle. So this is an example where the mirror reverse strategy actually fails. So with that, we prove the following theorem. If we let G be a game board with 180-degree rotational symmetry, and no edge and its partner edge share in the same cell, because that was the issue when we go back to look at this graph. This edge, AE, and its partner edge, EC, it shares the same cell. That created the problem for us. So if we restrict that from happening, we say that if there's no edge through the center of the board, then player 2 has a winning strategy. But if there is an edge, then player 1 has the winning strategy in this particular case. We also have results for reflective symmetry, which is similar to the results for rotational symmetry. So we're going to have the same. So in board A, both boards are reflective across some line, right? So in board A, player 2 has the winning strategy. And in board B, player 1 has the winning strategy. They'll begin by marking this edge E to B or B to E in whichever direction. And now they're going to use the same mirror reverse strategy. Whenever it's possible to win, to do so. But if it's not possible, then they're going to mirror the other player's strategy by observing their most recent move and playing the partner edge with its arrows reversed. We do need to have some restrictions for this reflective symmetry as well. As we can see in this next example, this graph has reflective symmetry, but looking at it, if we play the mirror reverse strategy, so if player 1 starts and they play the edge from A to D here, now they can mirror player 2's strategy. But in mirroring player 2's strategy, they actually create a death move. So if player 2 plays the edge from B to D, then player 1, mirroring the strategy, will play the edge from D to C, which creates a death move because now player 2 can play the edge from C to A and win the game. And so we need to restrict whenever the axis of symmetry, whenever there's an edge along the axis of symmetry, we need to also restrict that from our graph as well. I do want you to know though, this graph has rotational symmetry. And so we can use the rotational symmetry method for this graph, but I just wanted to give you an example of a graph that had reflective symmetry and where it didn't work. So here we have the following result. If we let G be a board that is symmetric by reflection across some line with no edges along the axis of symmetry, and at most one edge crossing the axis of symmetry, then on this board, player 2 has a winning strategy if there's no edge crossing the axis of symmetry. But if there is a single edge crossing the axis of symmetry, then player 1 has the winning strategy. What questions do we have about this? Okay. Now I want to talk about the following. Is it possible if we have the following question, or if we have the following graph? If we have a graph in which every edge of the board is marked, must there be a cycle cell? So here, that means that there are no unmarkable edge and every edge is marked. The answer to that is the following. If G is a finite board and it's connected such that there is no sinks and no sources and such that every edge is marked with an arrow, then G contains a cycle cell. To show that G contains a cycle cell, we find first a directed cycle that is not necessarily surrounding a cell, so it could be a larger directed cycle, and then we use an iterative process to produce successively smaller directed cells, which eventually leads to a directed cycle surrounding just a single cell, since the board is finite. So to do that, I'm going to talk about two lemmas that we use to prove this theorem. Before I do that, I should also give a definition because we're going to use this definition in our lemma. If we have a directed cycle gamma, this directed cycle is inside absorbing if E is an edge in that graph so if E is an edge in the graph G that lies inside the directed cycle and is incident to a vertex V on gamma such that the edge is pointing. So then you have the following. You have the edge U to V here for some vertex U. So we call this directed cycle inside absorbing. Using this, we have the following lemma. Oh, also it's important to note that cycle cells are vacuously satisfied, they are inside absorbing. Using this, we have the following lemma. The game board G must contain a directed cycle that is inside absorbing if all of the edges are marked. And to see this, we can do the following process. We can create a directed cycle, or directed path from U1 to U2 all the way up to UK in the following manner. Well, first, there's at least one directed edge U1 to U2 for some U2 since our game board contains no sinks and no sources. And so we start there. And by starting there, we use what we call the clockwise selection rule to select all of the other edges in our directed path. So we go in a clockwise direction, and we are going to select the first edge in which its vertex is pointing out. By selecting that first edge, now we have created a path from U1 to U2 to U3, and then we can select the vertices U4, so on and so forth in the same manner. At some point, by doing this, we're going to arrive at some vertex UK, which actually goes back to one of the vertices that we've already used in our path. And so this is going to create some sort of cycle. But there can be still things inside that lie inside here. And so now what happens with that? Well, we have the following. This is going to yield the directed cycle, so we know that, but it's either going to be a clockwise directed cycle or a counterclockwise directed cycle. It's counterclockwise if it surrounds a boundary region on its left, and it's going to be clockwise if it surrounds the boundary region on its right. If it is counterclockwise, then by construction, this is inside absorbing, and we're done. So because of our clockwise selection rule that we've used. But if it's clockwise, then our construction produced a cell with the property that every edge outside of that cycle is incident to a cycle vertex that must be directed towards that vertex. And so now, if it's clockwise, we're going to use this clockwise cycle to produce a new cycle that is inside absorbing using the following manner. We're going to start with this, but now instead of using the clockwise rule, we're going to use the counterclockwise rule to create that directed path. In doing so, what this does for us is that it creates, at some point, we're going to get an inside absorbing cycle, and we're guaranteed to get that by using that process because our board is finite. And then now we have the following lemma. Every inside absorbing directed cycle on a game board, G, either borders a cycle cell or it contains a strictly smaller inside absorbing directed cycle because of the way that we're using the clockwise selection rule as well as the counterclockwise selection rule, because we're always looking inside of that cycle to get the next cycle. So with these two lemmas, we can produce a sequence of progressively smaller directed cycles within our game board G. And since our game board G is finite, then this sequence must be finite, and then it'll lead to us creating an actual cycle cell. And so we're able to see that if you have a game board in which all of its edges are marked, then it must have a cycle cell. With that, I want to spend the last few minutes talking about some further questions. So here, can we determine other winning strategies for other classes of boards? So far, we've only looked at cycle graphs. We looked at the K4 board. We did spend a little bit of time looking at wheel graphs. So wheel graphs, if you don't remember, they look something like this. We spent a little bit of time looking at wheel graphs. For W5, so the wheel graph on 5 vertices is actually a little bit more trickier to prove than not. We do believe that there is a winning strategy for player 2 for the wheel graph on 5 vertices. But there are other vertices, there are other graphs that are interesting to do. My students and I actually last fall and spring, we worked on a class of graphs, and we did some coding for this, so this can be coded, but we're still unable to prove it for all classes of that particular graph, for all cases of that graph. So that's something that's interesting to do. Also, this is a question that I was interested in early on. What happens if we say that finishing a game without producing a cycle cell is considered a draw? Is it possible that we can have a win for every game board if that's the case? And if not, what else should we consider? And then on a larger game board, how does the game change in strategy if the object is to complete as many cycle cells as possible. And when I think about this larger game board and we're wanting to create as many cycle cells as possible, I think about playing this game. I called it dots and boxes as a kid, in which there are a bunch of dots and you draw lines, and the whole purpose of the game is to see how many boxes can you create. And so I think about that. So how can we do this thing? And then lastly, this game is already only played on two-dimensional cellular complexes, but what happens if we play this game on three-dimensional cellular complexes where the two-dimensional places are marked with an orientation? With that, I want to ask, what questions do you have?
Thank you so much. Maybe before we go to the question, we can all unmute ourselves and clap. Okay. Yeah. So, any question?
Is the class of graphs where your cells are edge disjoint, so like a 3-cycle with a 4-cycle joined by one vertex? Are those types of graphs sort of I don't think they're deterministic, but do those have a winning strategy?
So I'm working with students right now. So one of my collaborators, Dr. Carker, and we are working with 2 groups of students right now on this particular thing. We do have some results for some cyclographs, but then there are some cyclographs in which we're not able to do this. For example, if you're looking at 2 cyclographs that are odd and not necessarily the same cyclographs, so M and N odd and M not equal to N, it's not immediately clear that one player or the other player has a winning strategy. But if you're looking at some cyclographs in which you draw like 2 even graphs, for example, where the 2 even graphs, what they do have is they have a rotational symmetry. And so you can use the rotational result for that. You can also use the result for reflective symmetry, I believe it is, for if you have a graph, a cycle that's odd and a cycle that's even, then you can use the reflective symmetry. So we can use those results as well. Right now, the case where you have 2 odd or 2 even, we cannot use or 2 odd that are not the same. We cannot use the results that we have for symmetry because we'll have 2 edges along the axis of symmetry. And we don't have a result that says anything about the 2 edges that are along the axis of symmetry.
Okay, awesome. Thank you.
Shanise, I'm a little bit confused about the second bullet on this page. It says, how does the game change in strategy if finishing without a cycle cell is considered a draw? And so you have a theorem which says that if all the edges are marked, then there must be a cycle cell, right?
Yes, that's if all the edges are marked. But if we go back to the case where we have, I think here. How do I want to do this? Yeah. Oh, sorry. If we go back to this case, if you're looking at this graph, then not all the edges are marked and we now have a draw. So we're not considering the player to make the last move being the player who wins the game. So this is what we mean by a draw.
Oh, I understand. So what you're saying is that the game ends if there's no legal edge.
Right.
Okay, so the other question is anything known about the complexity of this game in general? Like, is it space complete or something like this?
So it's very new. We didn't actually look at the complexity, but that's also one of the questions that we have, like as a future question that we can look at, is the complexity. Okay,
thank you.
I have a question. You gave a result for 180-degree rotational symmetry. That's order 2. But you also did an analysis at the start for K4, which has order 3 rotational symmetry. Do you have any results about higher orders of rotational symmetry than 2?
Yeah, so we talk about graphs that have that are involutive. And so if their graph is self-involutive or part involutive or nowhere involutive, we have this result. So I gave you the theorems that I did for rotation and reflective symmetry are corollaries to this other theorem that says if you have a graph that is either nowhere involutive or it has it's self-involutive, then you can have a winning strategy for player 1 or player 2. And then the 180-degree rotational symmetry came from that theorem, as well as the reflective symmetry.
Thank you.
Mm-hmm.
I also have a question. So you said you programmed to see if the player has a winning strategy or not. How would you go about that? So how do you program that?
Right. So one of my research students actually created trees. So you created a tree diagram and it actually, you played the game with it. So you're either player 1 or player 2. The computer allows you to decide that. And then from there, the computer is always trying to play the optimal strategy if it's player 1 or player 2. That was the initial results. And so you create a tree. So for example, the graph that we were looking at was this graph. Oh, it's not perfect. But we were looking at this graph. And creating the trees, I think that on this particular graph, there were at least 10,000 trees and like 10,000 different ways that you can create it. And so what the computer program does is it goes through, after you mark a vertex, it goes through all the possible outcomes. Since the computer is always trying to play the most optimal strategy, it allows you to mark. So if you're player 1, it'll tell you which plays are optimal for player 2, but it'll also tell you whether or not you're going to win or you're going to lose. And so that's how we created it, just by using trees. And the trees look like a bunch of numbers, but it ran over a series of days. And so we tried to do it for this graph as well as this graph. We think about a pentagon as well. And then there's a lot more results. So that's what we did.
Okay, thanks.
Mm-hmm.
Hi, here's a question about the filling the board question.
Mm-hmm.
So I'm guessing is it somehow equivalent to a sort of edge coloring problem? So for example, in the graph, let's say you have like 9 vertices,
Mm-hmm.
and you label those 9 vertices from 1 to 9. And then, for example, if you want to draw an arc from a small vertex to a large vertex, then you color that edge in red, for example.
Okay.
And if you start from a large vertex to a small vertex, then you color that edge in blue, let's say. So is it possible to rephrase the filling the board question in terms of edge coloring? So you just do the edge coloring for your planar graph, so that you want to determine whether there's a monochromic cycle. Is that equivalent?
Yes. So I think that if as a first thought that I think about that, if I want to create this monochromatic cycle, then I would want it to, because I want to create a successively smaller cycles, then it may be I want a specific color, right? So if I'm going from a larger number to a smaller number, that may be what I want to be able to create that monochromatic cycle.
Okay.
Versus like if I just have some cycle, then if I just have some monochromatic cycle, I don't think it will guarantee that it creates a cycle cell, because ultimately I want a cycle cell. So I will want to know something else about how to create that.
Okay. Okay, got that. Thank you.
Okay, thank you so much. If there's no more questions, we invite each speaker at the end